Good morning, folks. Nasty weather, huh? But we will push on. So, before we get into today's material, I want to go over a couple of the quiz questions from last time. So 722. When you looked at this particular problem, or these two parts of the problem, one of the things that you need to keep in mind is it told you exactly what the mechanism was. It's SN2, right? So we know that the nucleophile is going to attack the carbon with the halogen. Okay, so that's number one. Number two, you have to be able to identify what the nucleophile and the electrophile are, right? And so we know that the alkyl halide is going to be the electrophile. We know that in this case, the sodium acetate is going to be the nucleophile. It's this oxygen atom, the oxygen atom with the negative charge, that's going to be the nucleophilic atom. Why is that? Why isn't it going to be like that carbon? Why is it going to be this?
Because it has a negative charge that can go into pair of electrons.
Yeah, it has a negative charge, right? This carbon also has a full octet. There's no electron pairs for it to react with anything. It's just there along for the ride. Okay? So several of you made a bond between this carbon and this carbon. We don't need to be doing that, right? So we've got this oxygen atom. The sodium, this is just a salt, right? The sodium has nothing to do with the reaction. It's just a spectator ion. So the nucleophile comes in, attacks that carbon, the leaving group leaves. And that would be the correct way, or you could have just written NaCl, that would have been fine too. Okay? So the sodium doesn't remain in part of the product. Okay? So these are not bound together by a covalent bond. It's just an ionic bond. So they're going to be spectator ions. So that is the product that you should have done. Again, now we've got an alkyl iodide and we've got a molecule. It's called a thiolate. Don't worry too much about that, but it's the negative charge, right, on the sulfur. Sulfur's a really good nucleophile. It's going to attack that carbon and the leaving group is going to leave, and we're going to end up with okay. I don't know why, but a number of you forgot to include that part on your answer. You just put a bond to sulfur, and it was just sulfur by itself. Remember, everything that's attached to the nucleophile goes with the nucleophile. We're not breaking any of those bonds. So you have to keep that in mind. Okay, so as you're working these problems, find the nucleophilic atom, and everything else that's on that atom is going to go along for the ride. Okay? Are there any questions about this? Okay. Also, don't forget, I sent an email. There will be a review session tonight at 5:30 upstairs in Tech 411. And there will also be one tomorrow at the same time in Tech 411. So that will be your opportunity to come and ask me any questions you have about the upcoming exam on Thursday. All right. We have got to wrap up chapter 8 real quick. And I didn't really have a good set of slides for this, so I'm just going to talk about this on the board. The last part of chapter 8 is on epoxides and thiols. And an epoxide is nothing more than an ether, and I'm just going to put an R group there, that happens to be part of a ring. Right, so if we look at this versus, let's say, diethyl ether, my favorite one, right? Looks like a bat. What's similar about those two? It's an oxygen atom that is singly bound to two carbons. An oxygen atom singly bound to two carbons. It is an ether, but it has a different name. It's called an epoxide, right? This is an ether. This is an epoxide. Okay? So there are some similarities, but there's also some very significant differences. If I take an ether, like diethyl ether, and I put in a nucleophile, for all practical purposes, nothing happens, especially for the purposes of this class. Ethers are fairly unreactive. Okay, and so we're able to use them in a variety of reactions because they're not reactive. They make good solvents. However, that's not true for an epoxide. If I take an epoxide and I put a nucleophile in there with it, it will react with that nucleophile. Can anybody suggest to me why that might be the case? Why might we see differences in reactivity? Why would an epoxide be more reactive than a regular ether?
Strain.
Strain. That's exactly right. If we try to build a model of an epoxide, and in our model kits, the red atom is an oxygen. So let's just imagine I've got two carbon atoms linked together. Okay, so I've got two carbons, and I'm going to try to put an oxygen and make a ring. Notice what's happening to my model kit. Right, as Barron said, it looks like there's a lot of strain there. In fact, you can see the bond starting to bow out. And if you open it, you can hear a big loud pop, which you don't hear if I just open up a normal bond, right there. So you can visualize that ring strain. It's called ring strain. And so it makes this molecule a bit more reactive, actually a lot more reactive than what you might expect to see for an ether. And so in fact, if you react these with a nucleophile, and let's just use our good friend cyanide. So let's say we have sodium cyanide. The sodium cyanide, this is going to be our nucleophile. It will react almost like an SN2 reaction. Very similar. It comes in from the backside, and the oxygen now functions as a leaving group because of that ring strain. And we've opened up that ring. So epoxides are very reactive. You all are probably familiar with some epoxides. Have you ever heard of epoxy glue? Right? It's an epoxide, very reactive material. Okay, and so this is how the epoxides are different from regular ethers. Okay, we learned that we can make regular ethers from that reaction called the Williamson ether synthesis. Right? In this case, we could use something like CH3, CH2, Br plus CH3, CH2O minus. Right? And this could be an SN2 reaction, and that would make the ether. That is not how we make epoxides. Okay? You don't use the Williamson ether synthesis to make epoxides. In fact, you make epoxides from alkenes. So if I start with this alkene, I'm going to end up with that epoxide. What do I need to add to make that happen? Look at the left and look at the right. What do I need to add to go from an alkene to an epoxide? Going from here to here, what do I need to add? Don't make it complicated, just look at the two structures. What do I need to add? I need to add an oxygen atom. Can you all go get a bottle of oxygen atoms? Now, you could get a bottle of molecular oxygen, the stuff that we breathe, but that's O2. There is no bottle of oxygen atoms that I can just get that will stick just an oxygen atom on the alkene. Okay? But there are reagents that will behave like that. Okay? And these are called peroxy acids. Kind of looks like a carboxylic acid with an extra oxygen. Okay? And these epoxy acids will react with alkenes to make epoxides. And your book talks about the different types of proxy acids. Any proxy acid will work. Okay? But they can work to make these so-called epoxides very, very easily. Okay? It's a very nice reaction. We've used it quite a bit in my laboratory a number of times. Works very, very well. Okay? So that's essentially what you're going to need to know for the test for epoxides. You need to know how we make them. We make them from alkenes and proxy acids. And you need to know that they are reactive. They can be opened up with nucleophiles. Okay? For the purposes of this class, we are always going to use nucleophiles that attack the carbon that has the most hydrogens on it. Obviously, this could have attacked either this carbon or this carbon, and there are special rules that determine, but you all don't really need to know that for the purposes of this class. If you want to know more about that, you can take my higher level class. Okay? But for the nucleophiles that we're going to be using, you're always going to attack this least hindered, if you will, carbon atom because it doesn't have the R group. So R can be anything, remember, right? So it could be a methyl group, it could be an ethyl group, it could be a ring, whatever. But the nucleophiles, for the purposes of this class, we're going to attack there. The other piece of chapter 8 is the thiols. And for the purposes of this exam, we're not going to cover a whole lot of this because I want to reserve the thiol chemistry for when we talk about proteins. That's where the interesting stuff that you all need to know comes in. And so it turns out that these thiols can be oxidized to make these so-called disulfide bonds where it's a sulfur-sulfur bond. And this plays a role in how your proteins hold their shape. Okay, so when you all are in your class talking about proteins and stuff, when you get into biochem, these things are really, really important. They're going to call them disulfide bonds or disulfide linkages, as some people call them. Very, very important concept in organic chemistry. But for the purposes of the exam on Thursday, that's all you really need to know.
So epoxides are made from the oxidation of alkenes. Is that what you said?
They are, by the addition of a single oxygen atom to an alkene, yes. Any other questions? All right. So let's get into today's stuff. And whatever we get through today is fair game on the exam. But today we're going to talk about aromatic compounds, benzene, the concept of aromaticity. When I say aromatic to you all, what do you all think about right now? Smell. Yeah, that's right. You know, you go into a nice restaurant and you might say, that's a nice aroma. Somebody might put on some nice perfume or cologne, you say, that's a nice aroma. This is not what we're talking about when we talk about aromaticity. Okay? This is not what we are talking about at all. But let's do a little bit of a thought experiment, then let's test that thought experiment. Let's suppose I have that molecule. How would you name that molecule? It's a 6-membered ring, so the parent is what? Yeah, it's hexene, right, because it's got a double bond. So this is cyclohexene. That's right. This is cyclohexene. It's got a carbon-carbon double bond. And if I react that with something like, let's say, bromine, I would expect that the bromine would add across that carbon-carbon double bond. We talked about that in the previous chapter, right? And so what am I going to get if I do that? How would I draw that? So I'm going to add bromine across the carbon-carbon double bond. I'm going to break the carbon-carbon double bond. I'm going to get 2 new sigma bonds. How would I draw the bromines? Will they be on the same carbon? Will they be on opposite carbons? They'll be on opposite carbons, right? So one of them will be on carbon number 1, one of them will be on carbon number 2, right? So you could draw it like this, right? And that would tell us something about what is happening. Is that everything though? No. And in fact, we know that one of the bromines will be coming out of the plane of the board at us, and one of the bromines will be going behind because it's a trans addition, right? They add on opposite sides of the carbon-carbon double bond. What do you all know about bromine? Here is a solution of bromine. What can you tell me about it? It's a liquid, okay. Bromine is a liquid at room temperature. This is a solution of bromine. It's not pure bromine. But what else can you tell me about it?
Highly toxic, highly reactive.
It's highly toxic, it's highly reactive. What else? Somebody said it. It's kind of a reddish brown, orangish kind of color. Yeah, it's got color to it. And that's because the bromine is bound to another bromine and it does some stuff with the electronics and light can absorb it and yada, yada, yada. You can learn more about the chemistry of color later. But it's colored. Okay, so bromine is colored. Cyclohexane, do you think it's colored or not?
No.
It is not colored. In fact, here's a solution of cyclohexane. It is clear. Okay? That it's not pure cyclohexane, it is cyclohexane in another solvent that's inert. But there's a lot of cyclohexane in there, and it's colorless. So if I take this colorless thing and I react it with this colored thing, what do you think I get as a product? Could have color, but where did the color come from in the bromine? Because I've got the two bromines bound together, right? Is that the case in the product? It is not. So in fact, I'm going to take something that's colorless, react it with something that's kind of reddish brown, and I'm going to get something that's colorless. So, colorless, color, no color. Okay? We're going to observe this. Now imagine that I take benzene, my good friend benzene. It too is a 6-membered ring. It's got 6 carbons in a ring. What's different about it compared to cyclohexene? It has more double bonds. It has 2 more double bonds, right? Yeah. What do you know about benzene? What do you think? You all seen those commercials about if you spend any time at Camp Lejeune, you know, you can file for a lawsuit. If you pay real close attention to that, it talks about benzene getting into the groundwater. So benzene is probably toxic. It's actually carcinogenic. I've got some right here in a vial, so it's not going to hurt us. But it's a solution of benzene. What can you tell me about it? It's colorless, right? Just like cyclohexene is colorless. They look identical, don't they? To our eyes. Okay. What would you predict would happen if I reacted this with a lot of bromine? What do you think could happen? We just saw that if I take one of the double bonds and I react it with bromine, I get a alkyl bromide, right? A dibromide. What do you think is going to happen here now that I've got 2 extra double bonds? What would your prediction be? What would you predict? Don't be shy. We're going to test it. We'll know the answer in just a moment. Take a guess. What do you think is going to happen?
Will it be different?
Might be, but we don't know. But what would you predict based on what you know from the top reaction?
Much more bromide will bind to it.
More bromine might react with it, right? You might expect that all the double bonds would react, and you would get a lot of bromine added to it. So I'm not going to show all of the stereochemistry here, okay, but you might expect that what you might get is a molecule that looks like this. Right? I've got a double bond, and a double bond. I know that double bonds do this. So why wouldn't this be reasonable? That's a reasonable thing to expect. Now let's test that. If this is true, right, we can test that. And if this is true, I would expect this to be colorless, wouldn't I? So what we're going to do, I'm going to put on some gloves here, safety first. And if I added just a little bit of bromine to one of these solutions, I would expect that the color of that bromine as it goes in would dissipate and become colorless, right? So let's see if that's true. So let's start with our cyclohexene and our bromine. And I'm going to come out here with it. I'm going to take a little pipette. Ooh, I can smell the cyclohexene. And let's see what happens. What can you tell me? It's colorless. Might have a little faint tint of color to it, but that's because I didn't put a lot of cyclohexene in there. But it went colorless, kind of as we predicted, right? So what do I have in solution? I've got this in solution right now, right? Now let's take benzene. A little bit of that. Woo. What can you tell me now? It's colored, isn't it? So what does that mean? What does that simple little observation mean? Okay, so I've still got bromine around, right? So did it react? If it's still colored, it means the bromine-bromine bond is still there, right? So did I break it? I didn't break that bond, did I? What's going on? This is not reacting to make this, as we might have predicted. No reaction. But wait a second, I thought I just told you that double bonds react with bromine, and we just demonstrated that a double bond will react with bromine to give a colorless solution. So what's going on? What do you think's going on? State the obvious.
Is benzene selective?
Okay, that's true. Not exactly where I wanted to go, but it's true. Benzene does not react, so there's some selectivity going on there. Okay, so the bromine-bromine bond must be more stable than the product. Okay, I'll buy that. What else? What other obvious thing aren't you saying? I must be telling you a little bit of a lie. Those must not really be double bonds. Right? I mean, if these are double bonds, then it should do this. But I drew it as double bonds. Right? This is a special class of molecules that are called aromatic. And while we draw double bonds in there, they do not behave like alkenes at all. And there's a reason for that we're going to talk about today. But what you should have said to me was, well, then maybe those aren't double bonds. And that's true. They're not normal double bonds. They are on sp2 hybridized carbons just like this is on sp2 hybridized carbons. But obviously they have different reactivity. The benzene still hasn't reacted. The cyclohexane reacted very, very quickly. I could add some more bromine right now and it would still stay colorless. And it would stay colorless until I added more bromine than there is cyclohexane to react with. Okay? So there's got to be something special going on with this molecule that we call benzene. It's called aromatic. It's called an aromatic ring. It's called phenyl group. There's a lot of names for it. But it's extraordinarily stable. Okay? And that has a lot of implications in terms of its reactivity and why it's important that we study this a little bit. Okay, so you just saw the demonstration, so we don't need to look at that. Okay? So, any structure that we draw for benzene has to account for these three facts. Benzene is planar, and in fact, let's make a model of benzene. There's a couple of carbons, there's a couple of carbons, there's a couple of carbons, and when I put these things together, right, they've got the double bonds all drawn into them already, and I put these things together, you'll notice that benzene is flat, right? I set it on the table, it lays on the table nice and flat. It doesn't form a chair, okay? It doesn't do the flipping stuff that we learned about for cyclohexane. It's a nice flat molecule, and you can see double bond, single bond, double bond, single bond, double bond, single bond as I got it built. Right, and what do we know about single bonds versus double bonds in terms of their length? What one's longer, a single bond or a double bond?
Single bond.
Single bond should be longer than a double bond, right? And so benzene should look like a short double bond, a long single bond, a short double bond, a long single bond, a short double bond, a long single bond. But is that what I see when I build the model? No. I see things that are the same distance. I'm using my fingers as a ruler here, right? But I don't have to go to get to that and then back, you know? They all look to be the same length. So what does that tell us about the single bonds? Are they really single bonds? They're not really single bonds. Again, this is one of the things that the model can't really show us very well. All of these bonds are actually the same length. Okay? All of these bonds are of equal length, which is kind of interesting. Right? If I take this and take it to my magic microscope, which we can do, and look at it, I would see that each carbon atom is identical. And the length between each atom is identical. Even though when I build a model, one should say one is longer than the other. And that's just not the case. Again, it's some of the strange stuff that comes out of these aromatic compounds. Okay? And so if I look at a carbon-carbon single bond, something like ethane, and I go in my magic microscope and I measure that carbon-carbon bond length, I would find that that bond length would be about 1.5 angstroms in length. Okay? About 1.5 angstroms, a little over 1.5 angstroms. If I look at a carbon-carbon double bond and looked in my magic microscope, I would see that the bond length is about 1.3 angstroms. And when I take my benzene molecule and look in my magic microscope, I would find that the bond lengths, all of them, are about 1.4 angstroms. Just about 1.4 angstroms. With those three numbers in mind, what can you tell me? What do those three numbers tell me? If a single bond is 1.5 angstroms and a double bond is about 1.3 angstroms, and I'm telling you that benzene's about 1.4. What can you tell me about the bonds in benzene?
Their constant residence.
That's a true statement. Getting ahead of it just a little bit, but that's where we're going with it. Pardon? It's in the middle, isn't it? It's somewhere between a real single bond and a real double bond. It's neither. It's in between because of resonance. I can draw resonance structures for benzene. That's what these arrows are, right? So, remember when we when we drew resonance structures earlier in the semester, we learned that we can push electrons. So let's assume that I don't move any of the atoms. I can push this double bond to here, I can push that double bond to there, and I can push that double bond there, and I can get another resonance structure that looks like this. All I've done is move the electrons around. And in fact, as he said earlier, it's constantly doing that. These electrons aren't really between these two carbon atoms or between these two carbon atoms. They are delocalized over the whole thing. Okay? So they act like they're a different kind of bond than we've ever really thought about. Right? They're not a single bond because they're not the right length. They're not a double bond because they're not the right length. They're somewhere in between. And these electrons are moving around that benzene ring all the time, and it actually generates current that we can measure. We can actually measure electrical current through magnetism, actually, in benzene. We see this in what we call NMR, and we'll talk about that in another chapter. Okay? But that's kind of cool, right? And it's because these bonds are in constant resonance. They don't want to react with anything. They're stable. Bromine, keep yourself. We don't care. We're stable enough as it is. Okay? And this stability of benzene is why it's a problem in Camp Lejeune. Even though benzene probably got spilled in the 1950s there, it's so stable it doesn't react with anything and it just stays in the groundwater. But if you ingest benzene, your liver can do stuff to it that makes carcinogenic molecules. Okay? If you smoke, you're inhaling benzene, by the way. And that's why you get some the cancer-causing effects of cigarettes and other tobaccos because of aromatic compounds, in particular things like benzene. Okay? There are a couple of ways in which we can name benzene derivatives, but benzene is always going to be the parent name for the most part. So for example, if I've got an ethyl group attached to benzene, we simply call that ethylbenzene. If I have a T-butyl group added on a benzene ring, we call that tert-butylbenzene. If I have a chlorine attached to a benzene ring, we call that chlorobenzene. Okay? If I have, let's play around here a little bit. What would I call that molecule? Bromobenzene. Yeah. What would I name it if it was like that? 1,2-dibromobenzene. That will work. There's actually some special naming with that can come into play. But yeah, you would be right. 1,2-dibromobenzene would be a perfectly good way to name that molecule. Okay? There are also some common names that have just stuck around. So if I put a methyl group on there, you all might say, well, that's methylbenzene. And if you answered that on an exam, I would count it correct. There's nothing wrong with that name. Nobody calls it that. They call it toluene. Anybody know what toluene is used for? Ladies? You may use toluene-based fingernail polish remover. If you buy a fingernail polish remover that says acetone-free, it usually either has ethyl acetate in it or toluene. If you buy paint thinner to thin the paint before you spray something with paint, it might be toluene-based. Toluene is a good solvent, very useful. And interestingly enough, I told you that benzene was carcinogenic. Toluene isn't. Or at least it's not as carcinogenic. It's generally considered not to be carcinogenic. So replacing a hydrogen on benzene and putting a methyl group on there all of a sudden makes all the chemistry different. Hydroxybenzene, that kind of looks like an alcohol, doesn't it? Kind of is, but it's different because it's attached to an aromatic ring. We call this phenol. Phen for phenyl. I told you that benzene was sometimes called a phenyl group. And OL for the alcohol. That's where we get the term phenol. Phenols are useful in a variety of things, but if you've ever used chloraseptic, the deadening agent that helps keep your throat from being so terribly sore, is a small quantity of phenol in the solution, or at least it used to be. I don't know if they've replaced it since then or not. And then aminobenzene. This is called aniline. Aniline is a very important industrial material. The clothes that you are wearing right now have color in them, in part because somebody did some chemistry with anilines to make dyes. So aniline is used an awful lot in the dye industry. Aniline is also used an awful lot in the explosives industry. So, good uses? Maybe not so good uses, right? And in fact, during the invasion of Iraq, if you go back and look, one of the claims that we made for that regime doing some stuff with explosives was the fact that we found aniline. And I remember going, so what? Aniline's used for a variety of different things. To me, it wasn't the smoking gun that they tried to make it out to be. Could have been used for that. Don't know. I know that aniline is very useful for a variety of things. Useful in pharmaceuticals, dyes, explosives. So it's got a lot of uses. Okay? So, if you have more than one substituent on benzene, like we did here, and as she mentioned, she would have named this 1,2-dibromobenzene, and there's nothing wrong with that. However, when you have two groups that are in a 1,2 relationship on a benzene group ring, we say that they are ortho to one another. This carbon and this carbon are they're ortho to one another. So this is ortho dibromobenzene. If I have the bromines in a 1,3 relationship, we say that that is meta. That is meta dibromobenzene. And when we have them in a 1,4 relationship, 1, 2, 3, 4, we say that that is para. That is para dibromobenzene. Okay? So let's look at a couple of examples. How are those groups in relation to one another? Are they ortho, meta, or para? Those are para. This is para-dimethylbenzene. How about that? Those are ortho. Right, that's ortho. And that is meta. That is meta-dichlorobenzene. You all ever gone to your grandma's house? And if she ever uses those little cakes of that smelly stuff that goes inside the toilet, you know what I'm talking about? The little thing hangs on the ring and it keeps the bathroom smelling from at least halfway decent. That cake is made out of para-dichlorobenzene. Okay? It's got that. That's where that odor comes from. Is para-dichlorobenzene is from that. So you all are familiar with these types of molecules. Okay? Have you all ever smelled mothballs? mothballs contain a molecule called naphthalene, which is an aromatic molecule. It's not benzene, but it's an aromatic molecule. Okay? So you know that you know that distinctive mothball smell if you smell it, right? Right? So you'll know this pretty easily. Okay? Let's look at a couple of interesting aromatic compounds. So here's one called benzo-A-pyrene. Don't worry about how you get the name for that. But what do you see when you look at that? Does that look like benzene? The whole molecule doesn't, but it looks like there's several benzenes connected together, doesn't it? Okay, and in fact, that's essentially what you have. This is called a polycyclic aromatic hydrocarbon. It's got more than one ring, if you will. That's where the polycyclic comes from. This comes from tobacco. When you burn it, you make benzopyrene, and it is a very carcinogenic product. Okay, you will, if you ingest enough of this, if you over your lifetime, you will get cancer. Okay, but there are other examples that we can show where we have benzene or aromatic compounds that actually have very good uses. Okay, this is Zoloft. Okay, this is a psychotherapeutic. It's used to treat depression and panic disorders. It was one of the first billion-dollar drugs back in the 90s. I think it and one other may have become the first billion-dollar profit drug. But you can see there's a benzene ring here, and there's a benzene ring here. Both are very important for them to have their psychoactive effects. It's a very simple little molecule. It's easy to make, actually, not hard, but very profitable. Here's another one. How many benzene rings do you see in this molecule? I see two. There's one here, and there's one here. This is diazepam, right? This is Valium. It's a sedative, right? Very useful drug. Okay? If you're getting ready to go to the dentist and they're going to give you a shot in the mouth, people usually freak out about this. They stick a stick in your mouth. You might remember that, right? With a little Q-tip on the end, and it deadens it before they give you the shot. It's this stuff. Okay? Novocaine or Procaine is the common name for it. It's a local anesthetic. Back when I was in your boat, we used to make this stuff in one of our labs. As an undergraduate, it was one of the things that you would make. You'd make Novocaine. And it's very easy to make from very, very cheap and inexpensive starting materials. They have since stopped doing that because even when I was doing it, if I got a little on my fingers, you could start to lose a little bit of your feeling for a little while. It would start to deaden your feelings, and you might sit there and work with a Bunsen burner or something and burn your fingers and not even know it. So we don't have students making these types of drugs anymore, unfortunately. Okay. This molecule, Viracept, nelfinavir. How many benzene rings do we see there? We see two. Would you call this one a benzene ring? I would, but I would also say it's a phenol because it has the OH on it. Okay? And then we have the benzene ring here as well. Okay, this is an anti-HIV drug, right? And you have to have these two benzene rings for this to be useful. Here's Viagra, sildenafil, right? You can see an aromatic benzene ring in this molecule as well. Okay, right there. And then Claritin. It's that time of year, right? Many of you, myself included, have allergies, right? You start to get stuffy-headed, all this kind of stuff. You have these seasonal allergies. This is an antihistamine. How many benzene rings do you see here? You do see one. This one is a benzene ring because it contains the 6 carbons. This too is an aromatic ring. We just haven't learned about it yet. It's called pyridine, and one of the carbons is replaced with a nitrogen. But it has 2 aromatic rings, but only one benzene ring in it. Okay, so you all were right about that. So these are some interesting aromatic compounds that you all may know, people who have taken. You may have taken some of these things yourself, right? Been to the dentist, you didn't want it to hurt too bad when they gave you the shot. They gave you a little Novocaine. Benzene was important. right? So I told you that benzene by itself was carcinogenic, and here we are giving it to you as Novocaine. But it's not a benzene ring by itself, is it? It's got other things attached to it. Okay? So whether or not we're talking about Zoloft or Claritin, right, when we start to put other things on benzene, it starts to behave differently, as we know. Should be the case. All right. So there are some rules to determine whether or not a molecule is aromatic. These are called the criteria for aromaticity, okay? And we're going to end off with what's called Huckel's rule. But rule number one, the molecule must be cyclic. What does it mean to be cyclic, practically? It means that if I put my pencil here and I go all the way around, I can get back to where I started without lifting my pencil. Right? If I do this, is that cyclic? No, because I start here. I now have to lift my pencil to get back to where I started. So is this aromatic? No. It has to be this to be aromatic. So the first rule is a molecule must be cyclic. Okay? The second rule is the molecule must be planar. When I build a model and I throw it down on the table, it must lay flat. If I add 2 more carbons to this, if I've got 2 more to add, let's see if we do it. There we go. This thing has seen better days. I can draw it flat. Cyclooctatetraene, the 8 carbons. Come on. They drew it flat, but when I build a model of it, notice what happens when I put 2 more carbons in here. I need to trim that way. Notice what happens when I try to lay it flat. There's a lot of strain in there, isn't there? You can see the bonds bowing. It wants to be like that. Just holding that in my hand and just barely moving it, it wants to pop into being this like boat shape or tub shape. Okay? Is that planar? It is not. Okay? So here's an example of something that looks like it might be aromatic, but it isn't planar. So it can't be. And in fact, if I took cyclooctatetraene and I reacted it with bromine, guess what? It would react. Suggesting that these things are nothing more than double bonds. Okay? The molecule must be completely conjugated, meaning I can draw an infinite number of resonance structures for it. Benzene is completely conjugated. It means that I have a p orbital on every carbon atom. Okay? So it is completely conjugated. And then the last rule, or last criteria, is Huckel's rule. It must have a particular number of electrons. And those electrons follow this formula. 4n plus 2 equal the pi electrons, where n is an integer, including 0. What is an integer? 0, 1, 2, 3, 4, 5, 6. It's a whole number, right? Talking about an integer. So how many pi electrons do I have in benzene, looking at this? How many double bonds do I have? I've got 3 double bonds. Each double bond has how many electrons in it? 2. So 3 times 2 is 6. So 4n plus 2 equals 6. 4n equals 4, right? Just do a little basic algebra. If I divide both sides by 4, n equals 1. So does it satisfy Huckel's rule? Yes. N is equal to 1. Okay? Must satisfy Huckel's rule. They give you the example of cyclobutadiene. Okay? If we were to make this, it could be flat. It is completely conjugated. There's a p orbital on every carbon atom. Okay? It is cyclic, but it does not satisfy Huckel's rule. It's got 4 pi electrons. 4n plus 2 equal 4. 4n equal 2. N equal 1/2. Does not satisfy Huckel's rule. It is not aromatic. In fact, this molecule satisfies the so-called 4n rule, which tells us if a molecule is anti-aromatic. We're not going to focus too much on anti-aromaticity in this class. But if aromatic is extremely stable, what do you think anti-aromatic is? Extremely unstable, extremely reactive. And in fact, to make cyclobutadiene, it's been made before, you have to make it at near liquid helium temperatures, or liquid argon temperatures, very cold, and it only exists for a few milliseconds. You can only observe it very, very quickly. It's highly reactive. Okay? So it's called anti-aromatic. All right. Each and every one of those 4 rules must be satisfied for a molecule to be aromatic. If you satisfy 3 of the 4, you're not aromatic. There's no such thing as partially aromatic. You either are or you aren't. Okay? So let's go over real quick. What are the 4 rules again? Must be cyclic. Must be planar. Must be conjugated, completely conjugated, meaning that there's a p orbital on every carbon. And what else? Satisfy Huckel's rule. And Huckel's rule is what? 4n plus 2 equals the number of pi electrons. Okay? So guess what? You probably are going to have a question about whether or not a molecule is aromatic or not on the exam. You can have your calculator. Okay? So you got to be able to count, you got to be able to do that kind of stuff pretty easily. But all 4 rules must be satisfied. So let's do a couple of examples here.
I didn't get that. Could you try again?
No.
Okay.
That's a pair of electrons. Aromatic or not? It is not. It is cyclic. Is it planar? I drew it planar, but if you built a model, would it be planar? No, it's not planar. Is it completely conjugated? Does every atom contain a p orbital? No. Do I even need to bother with calculating Huckel's rule? No, because the other ones aren't satisfied. How about this? Nope, not aromatic either. It is cyclic. It may or may not be planar, we don't know. It does have some conjugation. I can draw some resonance structures, but it's not completely conjugated. Not every atom contains a p orbital, so it's not. Benzene? Yes, we just learned about that one, right? And this is called cyclopentadiene anion. So I've got 2 double bonds and a negative charge on one carbon. Is that going to be aromatic or not? Is it cyclic? Yes. Is it planar? It is. I'll just tell you that. It is. So it satisfies that. Is it completely conjugated? I've got a p orbital here, 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 and here. We all agree with that? Okay, so 4 of the 5 carbons we know have a p orbital. And it turns out that this negative charge, these two electrons, are in a p orbital. So there are p orbitals on every carbon atom. Does it satisfy Huckel's rule? It does. 2, 4, 6. 4n plus 2 equals 6, n equal 1. Satisfies Huckel's rule. This molecule is also aromatic. Okay? And don't feel too bad. I didn't expect you to get that one correct. But I wanted to demonstrate some differences.
Will you do Huckel's rule right click on that last one again?
So I know that Huckel's rule, 4n plus 2 must equal the number of pi electrons. The pi electrons, I've got 2 here, and that pair of electrons is also, they're pi electrons, they're in a p orbital, 2, 4, 6. So 4n is equal to 4, n is equal to 1 when I do the math. Does that make sense? Just like benzene. Only it doesn't have. Let's try one more. Maybe 2 more. It looks like a sad face. Aromatic or not? Let's go through the rules. Is it cyclic? Yeah, it's cyclic. Is it planar? It has to be planar. Why does it have to be planar? Think back to your high school geometry. What do we know about 3 points in a plane? A plane must be defined by 3 points. That has 3 points, 3 carbon atoms. Those 3 points must lie on a plane. Okay? Mathematically, it must. So, cyclic, it's planar. Is it conjugated? P orbital, p orbital, p orbital. It's conjugated. Does it satisfy Huckel's rule? 2, 4, right? So 4n plus 2 equal 4. 4n equal 2. N equal 2/4, which is equal to 1/2. Does that satisfy Huckel's rule? No. It does not. It is not aromatic. In fact, this one is anti-aromatic, but you don't need to worry about that. Okay? What if I did this, though? And took that away and made that a carbocation on that carbon. It's still cyclic. It's still planar. It's still completely conjugated. Right? That carbocation, there's a p orbital there. There's a p orbital on every carbon. Does it satisfy Huckel's rule? Let's see. 4n plus 2 equal the number of pi electrons. I've got 2 pi electrons. So 4n equal 0. N equal 0. So does that satisfy? Or excuse me. Yeah. It can be 0, right? So 0, 1, 2, or 3. So if that does satisfy Huckel's rule, it is an aromatic compound. Okay? Let's continue on. What you're going to find, if you want to have something to write in your notes as opposed to the equation, N can be 0, 1, 2, 3, etc. And if those are true, then you're going to have this many pi electrons. 2, 6, 10, 14, 18, and so on and so forth. Okay? So we can have aromatic molecules that have more than 6 pi electrons. That's what we're trying to say here. These molecules are examples of these. These are called annulenes. They are aromatic compounds. They kind of look kind of funky, don't they? This is called 14-annuline. It's called 14-annuline because you got 14 carbon atoms in the molecule. Each carbon atom has a p orbital. It's cyclic, obviously. Take my word for it. If you built a model, it would lay on the table. It's planar. It's completely conjugated. Okay, every carbon atom has a p orbital. And there are 2 electrons in every one of those double bonds that are shown there. So there's a total of 14 electrons, right? That satisfies Huckel's rule. That is an aromatic molecule. 18-annuline is also an aromatic molecule because it satisfies Huckel's rule. Okay. Mothballs. The molecule is this, it's called naphthalene. It too is an aromatic molecule, but it has what looks like 2 rings attached to each other, and it is. But it is cyclic. I can start at 1 carbon, go all the way around and get back to where I'm wanted. If I built a model of it, it would be planar. Each carbon atom has a p orbital. It's completely conjugated, and it has 10 pi electrons. That satisfies Huckel's rule. It is aromatic. So if you ever go to your grandma's house and you smell in the closet, you smell that naphthalene smell to keep the moths away from for jackets and coats and whatever, it's that aromatic molecule that is the insect repellent. And it's a simple little molecule that looks like that. Okay. We just went through that. Okay. Now, I'm going to tell you just a little bit about molecular orbital theory. Did you all cover any of that in 106? You did a little bit of orbitals, right? A little bit. Well, you all know from at least what we talked about at the beginning of the semester that electrons don't really exist with atoms. They exist in orbitals, right? There's rooms that these electrons can go in. And if you did anything where in Chemistry 106 where you were having to draw molecular orbital diagrams, it probably made you go crazy because you really have to think about how the orbitals come together to make these new molecular orbitals. But it turns out it's real easy for aromatic compounds. All you have to do is be able to draw the shape of the molecule and draw a circle. Pretty simple. So the molecule of benzene is just a 6-membered ring, right? And if I draw a circle around benzene to where the circle touches each one of the carbon atoms, each one of these places that it touches becomes an orbital. Right? So here's the orbital, here's these orbitals, here's these orbitals, and here's this orbital. The rule is you have to have one of the points of the ring pointing straight down. That's the molecular orbital diagram for benzene, for the pi electrons. Okay, how many pi electrons do I have? For benzene, it's C6H6, it's got 3 double bonds, so how many electrons? 6. There's 6 electrons. So where would I start putting those electrons? At the bottom, right? So I've got 6 pi electrons that I got to take into account, so I'm going to put 1 here. Where do I put the next one? Do I put it here or do I go up here? What do we do? We're going to go ahead and put another one here spinning in the other direction, right? That's less energy than putting one up here. Now where do I put the next electron? I got 4 electrons I got to take care of now. Where do I put the next electron? Up here? Up here? Which one? The one on the left or the one on the right? In fact, that's a correct answer. If you said right, that's also a correct answer. They're equivalent, right? So I can do one on the left. Now where do I put my next one? I put it on the right. Now where do I put? I got 2 more to go. Now where do I go? Back to the left. I go back to the right. Notice there are no unpaired electrons in benzene, and they're all below this midpoint. That's really why benzene is aromatic. It's about the stability of the orbitals that the electrons reside in. They're very stable, they're very lazy, they're very happy there. They don't want to react. Why would you want to react? We're already as low in energy as we can get. Remember, reactions always occur to give things that are more stable, and it's hard to get anything that's more stable than an aromatic compound. That's why they're fairly unreactive. They're stable, okay? So, This is how you would put together the molecular orbital diagram for something like benzene. Okay? Benzene molecules have some special chemistry that you need to be aware of. You can take things like these alkyl benzenes, like toluene or isopropylbenzene, and you can treat them with a strong oxidant like potassium permanganate, and you can convert that carbon into a carboxylic acid. It's kind of a cool reaction. You can take toluene, and I've got a carbon that has some hydrogen atoms on it. I can treat it with potassium permanganate, and I get benzoic acid. I've converted this group into this group. Notice this molecule is very different than toluene. It's got more carbon, but it gives me the same product. These other carbons get oxidized away. Okay? The take home here is that you have to have a carbon atom on the benzene ring, and that carbon atom has to have at least one hydrogen. This carbon that is directly attached to the benzene ring is called a benzylic carbon. B-E-N-Z-Y-L-I-C, benzylic carbon. And as long as that benzylic carbon has at least one hydrogen, you can oxidize it into a carboxylic acid. How else have we learned to make carboxylic acids? Previous chapter,
Oxidizing alcohols.
oxidizing alcohols. What kind of alcohol?
Primary.
Primary. So I can take a primary alcohol and I can oxidize it to a carboxylic acid using which reagent? Jones reagent. Chromium trioxide, sulfuric acid, and water, right? We can do that. Well, here's another way that I can make carboxylic acids. I can take aromatic compounds that have benzylic carbons with hydrogen, and I can oxidize them to carboxylic acid. Turns out this is an important reaction. You can take this molecule diethylbenzene, react it with potassium permanganate, and you can get what's called phthalic acid. Phthalic acid is used in the polymer industry to make plasticizers, to make plastics behave like plastics and not be brittle. Okay? They make this by the oxidation of aromatic compounds. It's a big industry to make things. I mean, we all use plastics, and we all need these plasticizers to keep things from getting brittle. Notice this molecule, however, no reaction occurs. And why is that? Why does tert-butylbenzene not undergo oxidation? What's different about that benzylic carbon compared to the one on top? There are no what? What ain't there on this benzylic carbon compared to this benzylic carbon? Hydrogens, right? This just shows you that you have to have at least one hydrogen on the benzylic carbon for it to undergo oxidation. This molecule does not have that, okay? So, that is all we are going to do for today. This is where you're going to be held responsible for the exam. Is up through, what is this, 9.4, whatever it is. Know your rules for aromaticity, for sure. Be able to identify an aromatic molecule. Okay? Know those rules very, very carefully or closely, forwards and backwards. Write them down in your notes. So the exam is technically everything up to 9.4. Okay? Does that mean I can go back to other chapters? Not intentionally, but it's the stuff that we learned in other chapters still relevant? Absolutely. Right? But it's going to be from, where were we at? About 5.5, chapter 5.5, something to 9.4 or something like that. So that's all going to be fair game. It's going to be 25 questions and a bonus, just like last time. There will be a zip grade form that I will provide to you. You can have your notes, you can have your calculator, you can have your model kit. The only thing you can't have is your notebook or your textbook. You can't have access to the internet. You can't use your friends. Okay? So same kind of format as last time. However, there is no exam redo this time. So keep that in mind. Okay, you want to be very careful in answering your questions. Any questions about the exam? All right, well, study hard. Remember tonight, 5:30, this afternoon, 5:30, if you want to come by for some help up in Tech 411 upstairs. Have another session for that on Wednesday. Whether or not I record tonight depends on whether or not it is raining, because I'll be in my other office and I'm not carrying camera equipment in the rain. So I can't promise that I can record tonight, but I'll try to at least record one of the sessions if you can't make either one of them. Also, don't forget that I have office hours on Wednesday afternoons. So if you have any questions that you may want me to go over before the exam, please feel free to come to my office hours. Have a great day. Try to stay dry, and I will see you on Thursday.